You probably remember at least some part of atomic orbital theory from general chemistry. Remember, those were the different orbitals that electrons made up of. You could figure out the probability of finding your electron in a certain area of space, and that would give you your orbital. And so we have like the 1s orbital, which is the lowest energy orbital. And like other s orbitals, that's a sphere. And so the electron would be most likely to be found in that area. The p orbital is more like a dumbbell. And then there's d and higher energy level orbitals as well. But in organic chemistry, we mostly just stick with the s and the p. So those orbitals come out of the Schrödinger equation, and there's indeed solutions for this equation. And this equation is based on the idea that little tiny particles have both a particle and a wave duality, and they can act like waves. And so this is sometimes also called the wave equation. So, we have all these fancy equations and these beautiful diagrams of orbitals. And the way we end up representing those is sometimes in something like an atomic energy diagram, where that lowest energy 1s orbital, the one closest to the nucleus, is down here at the bottom, and then the other orbitals get higher and higher in energy. And like I said before, we're mostly dealing with the 1s, 2s, 2p orbital. So since this is organic chemistry, we're really focused on carbon. um, and indeed, that's what organic chemistry is, the study of. And so if we look at the atomic orbital diagram for carbon, what we see is, since carbon has an atomic number of 6, then that means that there are 6 protons in the nucleus, and then to have a neutral atom, you have to have 6 electrons. So we have our 2 electrons in the 1s orbital, and now, because the Pauli principle tells us that each electron has to have its own individual set of quantum numbers. Now this lowest energy level is full. There's just not any more room for more electrons. So we have more electrons left. So the next 2 go into the 2s. Now that's full. And the Hund's rules then tells us that for these degenerate orbitals of the same energy, it's lower energy to have those electrons in separate orbitals rather than paired in the same orbital. And the Aufbau principle, which we also use when filling this diagram, tells us that we start at the lowest energy and then fill until as we go up. Okay, so a common standard way of writing this atomic orbital diagram is as the electron configuration. You lose the information about the relative energy levels, but it's a lot easier to write on one line. So what we're talking about here is valence bond theory, and valence bond theory is kind of an add-on to atomic orbital theory to fix a problem. And sometimes when you have models, a problem will come up. You'll get an observation that doesn't match your theory, and then instead of throwing out the whole theory, you just kind of fiddle with it a little bit and try to make it match the observation. So that's what's been done here. If we look at this atomic orbital diagram, it suggests that since this orbital is half filled and this one's half filled, that means that carbon could form 2 bonds there, and then I'm not quite sure what would happen here. But it certainly doesn't match the observation that carbon actually forms 4 equivalent, same length, same strength bonds. So what valence bond theory does is it looks at the valence electrons and combines them to give these things called hybrid orbitals. And basically, you could think of some clay and imagine that some of your clay is 2s clay, like you've got a little sphere, you've got a dumbbell, and you smush them together, and then you divide them back apart, and those are your hybrid orbitals. They're like averages. It is energy-based, it's part of quantum theory, and one of the most useful parts of valence bond theory is that we use it all the time to distinguish between sigma and pi bonds and picture sigma and pi bonds. So in the last set of slides, we looked at geometry. And in fact, the easiest way to figure out what your shapes are of your different atoms in a molecule are is to look at this shape. And so if you have a tetrahedral atom, it's always going to be sp3. If it's trigonal planar, it's sp2, and it's linear, it's sp. It actually doesn't matter if that's oxygen or nitrogen or carbon. This is the case for all of them. So you do want to go ahead and memorize it. There are no exceptions to this, and it'll just make your life a lot easier if you do that. We can kind of uncover what these a little bit more and picture a little bit more about what these hybrid orbitals look like. And so this is an example of sp3 orbitals, and the sp3 orbitals here are shown forming sigma bonds, and so each of these carbons has 4 equivalent sp3 orbitals, and 3 of them are forming sigma bonds to hydrogens, and then one from each of the carbons is forming a sigma bond with each other. And so those sp3 orbitals are the average, or however you want to think about that, of these 3 p orbitals and then the s orbital. They're smushed together like clay and then divided out into 4 equal parts to give us those 4 sp3 orbitals here and 4 here. So this was my attempt to draw the lobes of the p orbital that's kind of left over. So I know this is kind of an ugly picture. I apologize for that. All right, so here what we are looking at is we're looking at each of these carbons has 3 sp2 orbitals, hybrid orbitals, and is forming 3 sigma bonds. And we can see those down here, and that's the combination of this 2s orbital and the 2px and 2py. And again, they're just kind of smushed together and divided into 3 different parts. And that's where we get our 3 sp2 orbitals. So 1, 2, and 3. And then those are bonded to hydrogens, giving us the sigma bonds over there. And then the sigma bond between the 2 carbons. The thing that's different between this one and the previous example, the sp3, is that this does have the 2pz orbital left over, which is what I try to show here. And so each of these carbons has one. Each of them has 1 electron in it, as you can see down here. So those 2p orbitals overlap to give you this pi bond, and it's not quite as good of an overlap as that sigma bond, so it's not as strong. It's a little bit longer, but it's still it's obviously a very important bond. One thing to notice is that this represents these red things over here represent 2 lobes of a single pi bond. This is not 2 pi bonds. This is just 1 pi bond. Now, in the case of an sp hybrid carbon, as we see here, now we have 2 pi bonds, and of course the drawing gets increasingly complicated. And now what's happened is we just have the 2s and then one of the p orbitals smushed together. We divide them in half. The carbon gets 2 sp orbitals, which it forms the sigma bonds with, and then it has the p orbitals left over that it forms those pi bonds with. All right, so as far as the practice, like what you'll end up doing with this is you will be identifying sigma and pi bonds and how many electrons are in each of those bonds. And then also figuring out whether you have sp3, sp2, or sp hybridization. So if we go look back at our caffeine molecule that we looked at in the previous couple of slides, this is tetrahedral, so it has to be this carbon over here to the left. So tetrahedral is sp3. It's got 4 sigma bonds. 1, 2, 3, 4. Carbon, it's got 1, 2, 3, that's trigonal planar. Trigonal planar. It's got 3 sigma bonds and 1 pi bond. So one of these is a sigma bond, the other one's pi, sigma, sigma. This is sp2. This nitrogen, it does have that lone pair there, remember? So it's also trigonal planar. And you can see that it's got, it actually doesn't have 3 sigma bonds. It only has 1, 2 sigma bond, a pi bond, and then it has a lone pair too.